us, or you?
I'm videotaping what I'm talking about so that I can show this the student. Okay, so we're going to talk about the difference between mass and weight, and I asked you to take that out in front of you. And so this handout basically provides an overview of what weight is and what mass is. And hopefully you recognize that weight is directly related to the force of gravity. So you have to have an understanding of what I mean, or what it is meant when we talk about gravity. Okay, so I'm going to first just give a quick overview of what gravity is. Okay, so actually gravity is an attraction between any two objects. And believe it or not, I know it's hard to believe this, but you pick two objects, any two objects, right? Pick them, name them, there's gravity between those two objects. So I think my example was Frank, my leopard gecko, right? And I said, there's an attraction between Frank and I, right? So in that case, I'm picking myself as one of the objects, and I'm picking Frank as the second object. There is a force of attraction or gravity between Frank and I. Now, does it feel like I'm being pulled towards Frank? And does Frank feel me being, feel that he's being pulled, or she, sorry, is being pulled towards me? No, of course not. We don't feel that attraction at all, right? And the reason we don't feel that attraction is because Frank's mass and my mass, or the amount of particles that make Frank up and the amount of particles that make me up, are so small in comparison to other larger or more massive things, that this attraction doesn't come into play. It's not felt, right? So you could pick any two objects, you and the desk, right? You and, your computer, whatever it might be, the person sitting next to you. There is an attraction between the people that you are sitting next to, you and the person that you're sitting next to, right? But you're not feeling it. So this force of attraction that I'm talking about becomes stronger when the objects themselves become more massive, and when the distance between the objects becomes smaller and smaller and smaller. Okay? So, let's start talking about then in examples where we actually do feel the attraction. And one that you are very familiar with is the attraction between Earth being one of the objects, and then any other object that you choose on Earth. Now, Earth is super massive, right? And we know that all objects are attracted to the very center of the Earth, right? And we know that this attraction gets greater the more massive the object that you're referring to, the more massive the object is with Earth itself, right? So somebody who has more mass than me has a greater attraction towards Earth. And we read that on a bathroom scale. We read that a person that is more massive than me, that has more particles, gets on a bathroom scale, and there's a reading that gives them a larger number, because they're more attracted to the Earth because they're more massive, right? Even though the distance between themselves and the Earth, or myself and the Earth, might be the same, the increase in mass makes them the attraction greater. Okay? Do you have a question?
Yeah, do you mean by attraction, you mean
There's an actual pull. So when I'm standing here on Earth, right, I'm being pulled towards the center of the Earth, but the Earth is being pulled towards me, too. It goes both ways, right? But the Earth is so massive that that slight pull that it is having to be attracted to me and all the other things on the Earth, right, it doesn't register, right? You don't see that. You don't see that. But we are both attracted directly towards each other. So pick any two objects, Earth being one of them, right? That second object that you choose is going to be attracted to Earth, and they will be essentially attracted to each other. Earth will be attracted to that object will be attracted to Earth. Okay? So this idea of gravity is one that's universal. It happens everywhere, but the larger the two objects, or one of those objects, is that you're referring to, then you start to feel the attraction, and the greater this attraction is. Okay, so it goes on to say that here in the United States, we measure this force of attraction. We refer to it as weight. And you know that, right? Because you weigh yourself. You use a bathroom scale to weigh yourself, right? And essentially, that bathroom scale has springs in it. Those springs are compressing depending on how attracted you are to the center of the earth. The more attracted you are, the more you compress the springs inside the scale, right? And the greater your weight is. Okay, so here in the United States, we measure weight using pounds. Okay, the rest of the world, essentially, aside from maybe some countries that are still using a really older system, like perhaps, I think, for example, some countries in Europe are still use things that are really outdated. Have you ever heard of a slug as a unit of measurement?
I've heard that.
Okay. Well, anyway, you can assume for now, just for the sake of understanding all this, that we in the U.S. use pounds, but almost all of the rest of the world measures weight in something called newtons. Okay, after Sir Isaac Newton, who is a famous scientist who discovered a lot of different things. Okay, so we're different because we measure things in pounds. The rest of the world measures weight, or the attraction between two objects, but they do it using the unit called newtons. And so there's a conversion that I gave you. For every 1 pound, right, that is equal to 4.448 newtons. Okay? So then that makes sense that if, say, for example, I weigh 150 pounds, right, my newtons is going to be 4.5 times greater than that. Right? So if you want to, I mean, maybe that's why the U.S. uses pounds. So they give themselves that image of having a smaller number for how much they weigh. Who knows, right? Maybe it's the obsession with having a smaller number. Okay? But essentially, they equal each other. So 1 pound equals 4.448 newtons. Okay, and then the reading goes on to say that, okay, so we're talking about Earth. So this is Earth, and we're talking about an object, say you on Earth. There's an attraction. You're attracted to the Earth. Earth is attracted to you. This is weight, which can also be the force of gravity, right? And we know we measure it in pounds, but the rest of the world measures it in newtons with a capital N. Right? Okay, so then it goes on to say, well, what about if you went to the moon? And the moon is about the 1/6 the mass of the Earth. So because the moon has a smaller mass, what is going to be the result if you were to go to the moon? If you were to go to the moon and you know it's 1/6 the mass, what's the result? How is it going to affect the force of gravity or weight? What do you think, Parker?
You're going to be a 1/6 what we wear on Earth.
Absolutely, right? You're going to weigh only 1/6, or a fraction of what you weigh on Earth, right? So you still have an attraction. In this case, we're talking about two objects, the moon and you. There's still a force of gravity, but that force of gravity is going to be much less because the mass of the moon is much less, okay? And so you're going to feel really light if you go to the moon. You would feel essentially almost as if you're floating. You wouldn't be completely floating, right? But, I mean, your steps would be really bouncy and light, right? And if you've ever seen any of that footage of taken with the expedition to the moon, you can see that in kind of what they've captured on camera. Okay, and say you went to a planet that was way more massive than the Earth. Right? If you went to a planet that was way more massive than the Earth, literally you'd feel crushed. Right? Like you probably wouldn't be able to stand up straight. Right? Because the force of gravity or that attraction would literally crush you. Right? And down, and your bones aren't meant to, your bones are meant to just overcome the force of gravity here on Earth, right? So your whole life, you've learned how to do everything that you do, your everyday life, in this particular gravitational field, right? So if you went somewhere else that had a greater gravity than the force of attraction, it would be really hard to move around, right? Because you would essentially feel like you were being crushed. Okay? Yes?
So you said that our bones are made for like this amount of gravity.
Yeah.
If you
And
went,
muscles?
if you went to the moon, would it be like worse on your bones?
Well, if you went to the moon and you stayed there, right, for extended periods of time, and this happens to people who go to the International Space Station, right, their bones become weaker, their muscles become weaker.
Would it be easier or harder to like walk?
When you first show up or after you spend time there? So when you first show up, you feel extremely light. Extremely light. But over time, you would lose bone mass most likely, you'd lose muscle mass, right? And then depending, I don't know how long it would take, but depending, you might not feel as light because now your muscles aren't as strong, right? So your body might adjust to the difference in the force of attraction. Yes?
But don't they have like special exercise machines built for space so that you can like,
Yep, so that you
it
can keep up
simulates
your...
like resistance so that your muscles can actually.
I have heard that, yes. So that they don't come, these astronauts don't come home like totally atrophied with their muscles like basically not being able to keep them up straight or upright anymore, right? That would be horrible. Yes.
So if somebody was on the moon, they would adapt their body.
I don't know how long that would take, and because we don't have, we haven't done that, we haven't spent extended amounts of time on the moon, like, you could probably look it up and see.
But like, if you went to a planet that had a 6 more mass, would you like gain muscle mass?
Maybe.
If you came back to Earth, you'd be like skipping 20 feet or something.
I wouldn't rule that out. I would say that your body would make adjustments, yeah, over time. I don't know how long that would take. Okay, and then the second part, so hopefully, does anybody have any questions still related to weight and kind of what, essentially, the basics of what weight is? So gravity is a force of attraction between any two objects. You have to pick the two objects you're referring to. That'll make it a lot easier to then kind of conceptually think about it, right? And there are different factors that affect that force, mass being one of them, how massive the objects are, the second one being how close their distance is between the two. So, of course, if you go up into space, first you go up into our atmosphere, and the further and further you get away from the Earth, the less and less of an attraction that you're going to feel, the less pull, right? Or if that force of gravity is going to be felt by you until you get out into space. And then there won't be really a force, right? And instead you'll be attracted to the other objects that are just around you. Okay? Kind of cool, right? Depending on their mass, of course. All right, so the mass then, we were talking a lot about the mass, but I want you to think of mass as essentially the sum of all the particles or atoms that make something up. Okay, so it doesn't mean that those particles or atoms are all the same size or, have the same number of protons, neutrons, and electrons. But if you were to take the sum of all of them, that would be the mass of something. Okay, so it's how many particles make up a certain object. And that number doesn't change. It's not based on gravity. It's not based on the force of attraction. So it doesn't matter where you are in the universe. That number will always stay the same unless you lose particles, right? Or you gain them. Then, of course, your mass will change. That number will change. But otherwise, it doesn't change depending on where you are. Okay, is that clear? Is that clear to you guys? And so, it talks about how the reason why a triple beam balance actually works in measuring just